Hello everyone. In this video, we'll be covering topics from the course of Chemistry 1412, also known as General Chemistry 2. So I'm going to go ahead and share my screen so that I can show you guys a PowerPoint presentation. All right, for this specific video, we're going to be covering the topics of intermolecular forces, solutions, and solubility. There are two types of forces, or also known as attractions, that operate in a molecule. There's intramolecular forces and intermolecular forces. Intramolecular forces are forces that hold atoms together within a molecule. So if we look at the image right here, we see an intramolecular force. So in between our hydrogen and our chlorine, we have a bond represented with the dark black line. So these are going to be the bonds such as ionic, covalent, or metallic bonds. We also have intermolecular forces, which are forces that exist between molecules. So not between the atoms or within the molecule, but it's what makes the molecule be attracted to another molecule. So it is what represents by this little dotted orange line. Intramolecular forces are items that we've covered in General Chemistry 1, but intermolecular forces are what we're going to cover in the General Chemistry 2 course. So although this is a very early topic, you're going to see this throughout the entire semester. There are 6 different types of intermolecular forces. There is dispersion or London forces, hydrogen bonds, ion dipole, dipole-dipole, ion-induced dipole, and dipole-induced dipole. So knowing the names isn't going to help you much, so we're going to go through and explain what each of these are. The first is dispersion or London forces. These are the weakest of the intermolecular forces. That is a key factor that you're going to want to remember as you're preparing for your exams. And exists between all types of molecules, whether ionic, covalent, polar, or non-polar. The more electrons a molecule has, the stronger the London dispersion forces become. Dispersion forces, or London forces, arise when the instantaneous dipole in one particle induces a dipole in another, resulting in an attraction between them. So before we kind of explain that, let me explain what a dipole is. So within a molecule, for it to be considered a dipole, it has to have a partially positive and a partially negative charge to it. So I guess the real world example of a dipole would be a magnet. So a magnet has a positive and a negative charge, and those charges are what attract items to the magnet. And so understanding the dipole will get a little bit easier as we go on through the rest of our forces. The next we have is hydrogen bonds. This is a special type of dipole-dipole interaction that occurs specifically between a hydrogen atom bonded to either an oxygen, nitrogen, or fluorine. And it has to only be those 3 elements that it can bond to. So right down here, we have something to kind of remember, or a trick to remember what a hydrogen has to be bonded to when it comes to the exam. So if you can remember, hydrogen bonding is FON, so instead of FUN, you have FON, which is fluorine, oxygen, or nitrogen. That is something that a lot of students use just as a little trick to help them remember when it comes towards the exam time. So when we look at our image right here, we have 3 water molecules, And as you can see, the oxygen molecules are partially negative, while the hydrogens are partially positive. The hydrogen bond, which is going to be represented by the orange dotted line, we see that our partially positive hydrogen is becoming attracted to the partially negative oxygen. And here's another example. We see this hydrogen that is becoming attracted to a fluorine over here, and we see that we have a hydrogen being attracted to the oxygen over here, but it can also attract to a nitrogen. The next is ion dipole. An ion dipole force is an attractive force that results from an electrostatic attraction between an ion and a neutral molecule that has a dipole. So your ions are going to be, going back to Gen Chem 1, either a cation or an anion. And then your dipole is going to be a polar molecule that has a partially positive and a partially negative charge to it. When you have an anion, which is a negative charge, it's going to be attracted to that partially positive charge of that dipole. And in reverse, if you have a cation, it's going to be attracted to the partially negative pole of that dipole. The next is dipole-dipole. These are forces that occur when the partially positive charged part of a molecule interacts with the partially negative charged part of its neighboring molecule. The prerequisite for this type of attraction to exist is partially charged ions. So in this case, both of them have to be a dipole for this attraction to take place. Dipole-dipole interactions are the strongest intermolecular force of attraction. So we can see a dipole-dipole in this image right here. So we have three molecules that are a partially positive hydrogen bonded to a partially negative chlorine. The dipole-dipole is when we have the partially negative chlorine being attracted to the partially positive hydrogen. Because both of them are dipole, you see the dipole-dipole attraction. Now we're going to get into induced dipoles. An ion-induced dipole attraction is a weak attraction that results when the approach of an ion induces a dipole in an atom or a nonpolar molecule by disturbing the arrangement of electrons in the nonpolar species. So we have a neutral molecule, which is represented by this little red circle. So as you can see, the circle originally has no positive or negative charge. It's chargeless right now. However, when we introduce an ion, so in this case we have a cation that is positively charged, it's going to induce a dipole in what was originally our neutral molecule. So because it is a cation, we're going to see a partially negative charge occur closest to the cation and the partially positive charge appearing farthest away from the cation. So the cation has induced or forced the once neutral molecule to become a dipole, and that is what an ion-induced dipole is. Now we have dipole-induced dipole. It's pretty similar to the ion-induced dipole, but now we have, instead of an ion, we have something that was already a dipole. A dipole-induced dipole attraction is a weak attraction that results when a polar molecule induces a dipole in an atom or in a nonpolar molecule by disturbing the arrangement of electrons in the nonpolar species. So, the dipole that already existed that is going to actually be inducing the neutral molecule to become a dipole is going to be polar. The item or the molecule that was neutral is going to be nonpolar. So we see our dipole, which is represented right here. It's going to come into proximity, or it's going to approach the nonpolar or neutral molecule, and it's going to force it to become charged. So because our dipole was partially negative and it's approaching, it's going to force the side that's closest to it to become partially positive. And that is the dipole-induced dipole. So there are a couple other items to consider. The shape of a molecule will affect the attraction forces. So for instance, longer chains means that a molecule has more surface area, resulting in a stronger intermolecular force. So if you have a question that you have multiple choices to choose which one has the strongest intermolecular force, and you have a bunch of different length carbon-hydrogen chains. So if you have carbon-hydrogen, and then you have one that has carbon-hydrogen, carbon-hydrogen, and it just keeps on building, you're going to have to pick the longest chain for it to be the strongest intermolecular force. So let's work through a couple examples. Example 1. The strongest intermolecular interaction between hydrogen sulfide, which is H2S molecules, arise from, and then you would have to be able to choose which intermolecular force is strongest within this molecule. So let's look at a couple things. We know that this molecule has no ions because we don't see any, which means that automatically we can cancel out D as an answer. We also know that there is no hydrogen bond because, remember, hydrogen bonding is fun, so it has to be attracted to a fluorine, oxygen, or nitrogen, and we don't have that, we have a sulfide. So it is not a hydrogen bond. We now have London dispersion, or we know that London dispersion is the weakest force and that dipole-dipole is the strongest, and because we do have a dipole-dipole force in our H2S, we know that A would be the answer choice. So the best way to work through questions like this is to determine what you do know about the molecule and cancel out all of the answer choices that just do not make sense. Now let's do another. So example 2. Which intermolecular force is seen in the interaction between O2 and water? So a couple things that we know. We know that O2 is nonpolar, and we know that water is polar. The O2 is a dipole because it is not a dipole, because it has two of the same elements. So remember when we had the chlorine attached to another chlorine, it originally had no charge, and that's because it is two of the same element. However, the water does have a charge. Remember that the oxygen is partially negative while those hydrogens were partially positive. So as our water goes and approaches our O2, it's going to induce a dipole within the O2, meaning that the only thing that we can have is a dipole-induced dipole. Now we're going to move on to solutions and solubility. A solution is a homogeneous mixture and exists as a single phase. Within a solution, there is both a solute and a solvent. Solute is what dissolves in the solvent to form a solution. Usually, the solvent is the most abundant component. So try to think about salt water. So I have a glass of water and I have some just normal table salt. Your solvent, which is the thing that does the dissolving, is going to be your water. However, the solute, so the item actually being dissolved, is your salt. When you mix those two together and it becomes salt water, that is your solution. Now on for solubility. The solubility, known as S, of a solute is the maximum amount that dissolves in a fixed quantity of solvent at a given temperature. Substances of similar intermolecular forces will dissolve in each other. Remember that like will dissolve like. Now we're going to talk about dual polarity and effects of solubility. We see dual polarity in alcohols, which means that it's going to have both a polar and a nonpolar side. So if we look at the general formula of alcohol, which is CH3, CH2, N, which is just going to represent a number, it'll be different for each alcohol, OH, and that is our general formula. The OH group for our alcohol is going to be the polar side, while the hydrocarbon group is going to be our nonpolar side. By knowing the polarity, you are able to determine if a substance is soluble within each other. So for instance, if I have another polar, say solute, and we put it in alcohol, the polar side, which is the OH group, is going to be able to dissolve that solute. So now I'm going to exit the PowerPoint and show you a brief video of some examples before I have you work your own.
Here's a question for you. Which of these two gases, carbon dioxide versus sulfur dioxide, which one has a higher solubility in water? Which one's more soluble in H2O? Is it CO2 or is it SO2? Now, water is a polar molecule, and like dissolves like. So the molecule that is more polar or that has more intermolecular forces between itself and water, that's going to be the one that has a higher solubility in water. Now, if you were to draw the Lewis structure of carbon dioxide, it is linear. Even though it has polar bonds, it has a dipole moment of 0. So CO2 is nonpolar. Now, SO2, if you draw the Lewis structure for that, it has a bent shape, and as a result, this molecule is polar. And so sulfur dioxide will have a higher solubility in water than CO2. Between two gas molecules, the one that's more polar is the one that's going to have a higher solubility. Now, what if you have two gases that are nonpolar? Let's say hydrogen gas and carbon dioxide. Which one is more soluble in water? Now, hydrogen gas is completely nonpolar. It's nonpolar as a molecule, and it doesn't have any polar bonds. Now, even though carbon dioxide is nonpolar as a molecule, it does contain polar bonds. Oxygen is much more electronegative than carbon. So oxygen bears a partial negative charge, and carbon bears a partial positive charge. A second reason why carbon dioxide is more soluble in water than H2 is because it's heavier. Heavy gas molecules have more London dispersion forces than lighter gas molecules. So carbon dioxide will have more forces of interaction between itself and water than H2 and water. So that's the second reason, it's heavier. The third reason is that when carbon dioxide is placed in water, even though carbon dioxide is a gas, it reacts with water in the form of carbonic acid. And carbonic acid is soluble in water. If you draw the Lewis structure of carbonic acid, notice that it contains hydrogen bonds. So it can form hydrogen bonds with water. So that's another reason why carbon dioxide, even though it's nonpolar, it's more soluble than H2.
What does it mean to be a music reporter? It means getting the right shot.
Let me go ahead and go back to our PowerPoint. So now that you've seen somebody else work an example, we're going to work a couple of our own. So we want to know, will ethylene glycol be more soluble in hexane or water? And we're given the formulas for both ethylene glycol and hexane. Water, hopefully you know, is H2O. So a couple things that we have to determine. So we know that ethylene glycol has two OH groups. We can see them right here. Here's our first one. Here's our second, meaning it can either interact with water, forming a hydrogen bond, or it can interact with hexane, forming a dipole-induced force, or dipole-induced dipole. So we have to determine which one is our strongest intermolecular force. Whichever one is has our strongest force is going to be the one that allows it to be more soluble. So now you're trying to determine, is a hydrogen bond stronger or is a dipole-induced dipole force stronger? We know that hydrogen bonds are stronger than dipole-induced dipole, which means that ethylene glycol is going to be more soluble in water. All right, now we're going to move on to factors affecting solubility. So, a couple of the factors, the first being temperature. Solids are going to be more soluble at a higher temperature, while gases are less soluble at a higher temperature. When it comes to pressure, it's going to only really affect gases. So a gas is going to be more soluble at a higher pressure, which helps us get into the topic of Henry's law. Henry's law allows you to calculate the solubility of a gas. It states that the amount of gas that dissolves in a liquid is directly proportional to the partial pressure of that gas. And this is going to be represented with the formula for Henry's law. So we have S gas, which is solubility of the gas, equals KH, which is a constant, times P gas, which is partial pressure of a gas. Do keep in mind that the KH will be different for each gas. It's not going to be the same for every single one. Sometimes you'll also see that S gas, or solubility, will sometimes be represented by a C if you're trying to look up videos on Khan Academy or anything like that. Sometimes they use the letter C to represent solubility. Another item that you do need to keep in mind is the units that each of these will be in. So solubility is going to be in moles per liter. Henry's law constant will be in moles per liter times ATM. And partial pressure will be in ATM. So now we're going to work a couple examples so that you can get used to working problems for Henry's law. So we have methane has a Henry's law constant, K or KH, of 9.8 times 10 to the negative 2 moles per liter times ATM when dissolved in benzene at 25 degrees Celsius. How many grams of CH4 will dissolve in 3 liters of benzene if the partial pressure of CH4 is 1.48 atm? So let's kind of take note of what we know. So we know that our KH is going to be 9.88 times 10 to the negative 2, and that's moles per liter times ATM. We also know that our P, or P gas, is going to be 1.48 atm. And we know that we're given, so I'll put volume, we're given a volume of 3 liters. And, and we want to know how many grams of CH4 we have. So I'm going to go ahead and exit this and move over to my boogie board. So I went ahead and I wrote down everything that we know from the question. And then you also, it's always good to form a habit of writing what the equation itself is. All right. So this one, when you just plug it in, it's not really going to give you the answer right away. So we're going to have to work through a couple different steps to be able to get to our final answer of grams in CH4. So what we do know is that to be able to get to grams, we first need to find moles of CH4. And we notice that we have the units of moles. So we have to be able to work to get our moles by itself. So we know that, let's go ahead and write it down here, F gas is going to be in moles per liter. We see that our KH is in moles per liter times ATM, and we know that our P gas is in ATM. So let's go ahead and plug it into our Henry's Law question and see what units we'll have after everything else cancels out. So we don't have F gas because we weren't provided it. So we're going to plug in what you have, which is KH and our P gas. So we say that S, which is solubility, equals 9.88 times 10 to the negative 2 moles, and that's going to be over liters times ATM, times our ATM, which is 1.48 ATM. So because they're across from each other, we can cancel them out. So we know that our F gas will be in moles per liter, which is correct. So you have to plug in 9.88 times 10 to the negative 2 times 1.48. And you should get a solubility of 0.146224 moles per liter. I went ahead and I wrote out a large amount of decimal places just so that I have something to work with as I move on, because we know this is not our final answer. We have moles per liter, but I need to get just moles so that I can convert it into grams later. So what can I use? I can use the volume that they provided us. So if you set it up on a reaction table, so we set up our solubility, so 0.146224 moles per 1 liter, because that's what this means. And we said that we have 3 liters. Our liters will now cancel out and we'll be left with just moles. So now you're going to multiply your solubility times the 3 liters. So this will give you, I'm going to go ahead and write it down here so I have more space, 0.438672 moles of CH4. But that's not what we're looking for. We're looking for grams. So we now need to set up a second reaction table to be able to get grams from this moles. So this, we're going to do the same thing that we did in General Chemistry 1. We'll take the molar mass. So CH4, if you look on the periodic table, it's pretty much around 16 grams per mole. So we say 16 grams per 1 mole of CH4, sorry, I wrote a 3, 4. We cancel out our moles and we multiply across and we'll get grams. So you'll do the 0.438672 times 16, and we'll get 7.02 grams of CH4. And this would be our answer. All right. We'll go ahead and clear this, and then we'll move back to our PowerPoint. So now we have a second example. This one says, how many grams of carbon dioxide gas is dissolved in 1 liter bottle of carbonated water if the manufacturer uses a pressure of 2.4 atm in the bottling process at 25 degrees Celsius. If the KH of CO2 in water is 29.76 moles per liter times atm at 25 degrees Celsius. Oops, sorry. Let's go back. They're actually both labeled example 2. All right, so here is another example. It's going to be pretty much similar to our first example. So we know that we have a volume of 1 liter. We have a pressure of 2.4 atm, and we have a KH of 29.76 moles per liter times atm. And what we want to know is grams of CO2, which is carbon dioxide. So I'm going to go ahead and exit this. So just like before, we set it up, and we'll write in what we have. So we know S gas equals KH times P gas, and we'll plug everything that we do have in. So just like before, we first have to solve for S gas. So we say solubility equals 29.76 moles per, let me go ahead and write it down here, per liter times atm times 2.4 atm. Just like before, our atms will cancel out, and we will multiply to be able to get our solubility. So we have a solubility of 71.424 moles per liter. But we need to get moles by itself, so we can multiply it times the volume that it gave us, which was 1 liter. We'll set it up on our reaction table. We have 1 liter. Our liters cancel out. You're just multiplying by 1, so you'll end up with the same number. So 71.424 moles of CO2. But we don't want moles, we want grams. So now we're going to convert from moles to grams. So we have 71.424 moles of CO2. Sorry, it's a little crooked. And we'll look at what the molecular weight is, which is around 44.01 grams per 1 mole of CO2. It's going to give us a pretty big number. Our moles will cancel out, and you'll do the 71.424 times 44.01. This will give you around 3,143 grams of CO2. And that would be your answer. So this one's set up the exact same way as our first example. So now we're going to go back, and we're going to work something that is a little bit different. So for this one, it says the solubility of a gas is 2.1 times 10 to the negative 4 moles per liter times atm. at 345 torr to increase the gas solubility to 4.5 times 10 to the negative 4 moles per liter times ATM, what should the partial pressure of the gas be for the above solution? So this one is slightly different. We now have to solve using Henry's law, but we have to do it twice because we have two different sets of information. So let's go ahead and write down what we have. So we know for our first set, the solubility is 2.1 times 10 to the negative 4 moles per liter times ATM. And at that solubility, our pressure equals 345 torr. We don't know what our KH is for this set yet. Now we want to increase the solubility, so our second solubility is going to be 4.5 times 10 to the negative 4 moles per liter times ATM. And that's all it gives us for the second set. They want to know what the pressure is for that second set. So I'm going to go ahead and escape and go over to our boogie board. So this is the information that they gave us for this problem. So what can we do to solve this? Well, we know that it's the same gas because all we're doing is increasing the solubility. So whatever our KH is for our first one can also be used for our second set. So our schema maneuver for this problem is going to be to determine what the KH is for our first set and use that KH to plug into our second set to be able to define the variable of pressure. And that's how we'll be able to solve for this problem. So first thing, write out our equation. And now we can start to plug in all the information. So we know our solubility is 2.1 times 10 to the negative 4 moles per liter times ATM equals KH times P gas, which right now is 345 torr. However, let's say for this example, we want to know what the pressure of P2 is in ATM, which means that we would have to first, before plugging it in, we'd have to convert our pressure from torr to ATM. So what we do is we take the 345 torr and we will convert it to ATM. So 345 torr, and we know that for every 1 ATM, we have 760 torr. So what we're going to do is plug in 345 divided by 760 torr. And this is going to give us 0.455 ATM. Because our torrs will cancel out. Cut it off a little bit, 0. There we go. So we can now plug this 0.455 into our equation. Now, we need to manipulate our equation. So we know that our KH and our pressure are multiplying, so to get it to the other side, we have to divide. So you'll do 2.1 times 10 to the negative 4 divided by 0.455 to be able to get KH by itself. When you do this, your KH will equal 4.615 times 10 to the negative 4. We can now use this KH to solve for our second set of data. So we're trying to solve for pressure. So we take the 4.5 times 10 to the negative 4 moles per liter times ATM equals our new number, which was our KH. I'm going to have to write it right down here. So this equals 4.615 times 10 to the negative 4 times our P gas. So just like before, how we divided to be able to get our KH by itself, now we're going to divide to get our P gas by itself. So you'll do 4.5 times 10 to the negative 4 divided by 4.615 times 10 to the negative 4, and that will get your P gas by itself. So when you plug this in, P gas is going to be 0.975 ATM. And that would be our answer. All right. So let's go ahead and wrap this up and start to go over everything that we've covered so far. So the first topic that we covered was intermolecular forces. In this, we covered each of the 6 different types, and we saw an example of each one. Remember that these are going to be seen throughout the entire semester, so you might as well go ahead and start learning them now. We also covered solutions and the difference between a solute and a solvent. This is also going to be used throughout the semester. I believe you'll also see this in topics seen when it comes to molarity, molality, and topics like this. You're now we now covered solubility, so we covered the factors affecting solubility, and we worked a couple examples from Henry's law. Henry's law can be, it's going to be one of the easier calculations. However, it does take some time, and you have to make sure that you really pay attention to units. Other than that, that is all that we are going to be covering for today. All right. Have a great day.